So in this last part of the video, we discuss Russell's paradox. Okay, paradox means a perplexing situation where you cannot decide whether this is true or something else is true. I mean, you are stuck. It's like a dead end. So that is a paradox. Now, Russell's paradox actually brings out the deficiencies of intuitive set theory. In intuitive set theory, what we have seen so far is that most of the sets that we have encountered can be easily dealt with using only our intuition. Intuition means just the notion that sets are collections of objects. To make this more precise, we have introduced the concept of well-definedness, right? I mean, not just any collection of sets is, any collection of objects is a set. It has to be well-defined. But is that enough? Russell's paradox shows that actually that is not enough. Although, to get to this paradox, we have to consider rather large sets. The kind of sets that, or the kind of collections that do not normally arise in the ordinary parts of mathematics that we have seen so far, which is almost nothing. I mean, we are yet to see many things like algebra, analysis, topology, higher parts of geometry, things like that. But there also we will see that we do not consider the kind of largeness that we will consider here, that leads us to something problematic, which says that the definition of sets that we have started with, that a well-defined collection of distinct objects is called a set, in some situations that is not enough. So this is an extreme case, and although it is not really useful in ordinary mathematics, but it nevertheless is of some interest in mathematics and is of great interest to logicians whose job is to study set theory in great detail. Okay, the things we have seen so far in set theory, that is just the bare minimum, that almost does not scratch the surface also. There are many more things in set theory which are quite deep and which, strictly speaking, do not form a part of mathematics. Okay, they are a part of logic. Anyway, so what Russell's paradox starts with something which we already know, namely one of the ways we specify sets, that is the rule method or set builder method, which, if you recall, was something like this, where what we do to specify a set, we specify a general element, right? And then we, after that, we put colon, which means such that, and then we write a condition that we, or a restriction that we put on x, that x has to satisfy. That way we identify those objects which will make the set. Okay, for example, it looks like this: p of x is true, right? So we have assumed that this way of specifying a set always gives us sets. For example, we can take some simple examples. X such that x is a real number and x squared is equal to 1. Okay, for example, this collection, and what the rule method says is that any such collection is a set, right? So that we have been using everywhere, right? And in this case, Px is this statement. Px is a statement involving x. Okay, it is a statement about x. X belongs to R and x squared is equal to 1. This is the statement Px. Now for which x is this statement true? It is true for -1 and 1. In other words, P of 1 is true and P of -1 is true. And that's why this collection equals this set. Okay, there is no problem with this. We can see that this collection actually has two elements. So it is a well-defined collection of distinct objects. So this is a set. Now, you can also consider another example such that x belongs to R and x squared plus 1 is equal to 0. Now you know that actually there is no real number which satisfies this equation, right? That is because the square of any real number has to be non-negative. For this left hand side to be 0, x squared has to be equal to -1. That is only one option. And that cannot be true for any real x. So there is no element in this collection. So this collection is nothing but the empty set. So in this case also, although it is empty, it is a set. Now the question is, can we take any statement in place of Px? Right? That is the question. And if we explore this question and take it to its limit, stretch it to its limit, then we come across a peculiar situation. That situation leads us to Russell's paradox. And that situation is this. You consider this statement. X is a set and X does not belong to X. Is it a legitimate statement? It is, because if you are, okay, let us try to see what Px says about some particular x's. For example, I can take x equal to 1. Okay. For x equal to 1, what is Px? Px is, P1 is this statement. 1 is a set and 1 does not belong to 1. Is this statement true? It is not true, because 1 is not a set. We don't even bother about this nonsense. Okay, first of all, it's a conjunction. 1 is a set and something else. Since the first statement in the conjunction is not true, so the statement is not true. So this is false. Okay. If instead of that we take x equal to 1, or we can take this one, then what about this statement? It says this is a set and does not belong to 1. Okay. What about this? Now, unlike the previous one, here this is actually a set, a singleton set consisting of only one element. And what about the second one? The second one is a rather peculiar condition which says that x does not belong to x. That is, x does not contain itself as an element. We have never seen anything like that. For example, the sets we have seen so far, like the set of natural numbers, the set of real numbers, these are all infinite sets. Have we ever seen anything like this? N belongs to n, which means that in the set of natural numbers 0, 1, 2, 3, do you get n anywhere as an element? No, because that's not what natural numbers are. They are numbers. No element in this set is itself a set. Okay. Although we have seen some sets where some elements are sets, but we have never seen a set in which the set itself is contained as an element. Okay. So, although this looks peculiar, but this is true nevertheless. Nowhere have we seen a set containing itself as an element. So, in this case, this statement is true. Okay. Now, for this Px, if I consider this set, for this particular Px, if I consider the set T, x such that Px is true, that means x is a set and x does not belong to x. Okay. The assumption that rule method always gives us a set, that assumption tells us that T is a set. T is a set. Now, in T, what about these two things? 1 does not belong to T. Why? Because first of all, 1 is not a set. So the first part of the condition itself is false. So 1 does not belong to T. However, this belongs to T. Because it is a set and it does not contain itself as an element. In fact, you can see that pretty much all the sets we have seen so far, they are all elements of T. Okay. And T is actually extremely large. It contains all sets that we have seen so far and many more. I mean, all ordinary sets or all sets actually that we have encountered so far are elements of T. T is that large. Now, we know one thing from the beginning of this set theory, intuitive set theory, is that something, any object, and if you have an object and a set A, suppose x is an object and A is a set, we either have x as an element of A or x not as an element of A, but we never have both of the things together, right? It cannot be the case that x is an element of A and at the same time x is not an element of A. This is sheer nonsense, right? Something will either be inside A or outside A. Now we try to decide this for A equal to T and x also equal to T. Whether T belongs to T or T does not belong to T. Okay, this we try to decide for this set T, which is a set according to what? You see, according to the rule method. Okay, this is a set which says that any collection of objects which satisfy a given property is a set. Now we will explore this question. You may think that this is automatically false because we have never seen anything like this. But we should not base our judgment on just intuition, although it is intuitive set theory. We should not just simply say that something is wrong because we feel it is wrong. Feelings have no place in mathematics. I mean, you can feel about something and try to create some new mathematics, that is an entirely different thing. But once you try to write down the axioms and try to do the calculations, you have to be exact. Okay, there should not be any ambiguity about anything that you are doing. So we have to explore whether this is true or not using only logic. So in this type of situations where we are not sure what the case is, usually we suppose by assuming that what is given is true or false. Actually, most of the cases we assume it to be false. That way we can get a contradiction. However, this is a special case and it is somewhat outside of mathematics. Okay. So we suppose this is true. Suppose T belongs to T. Okay. Now, T belongs to T means what? T is a set. So you see that in place of X, if we take T, this part is true, this part of the statement. However, this is not true clearly because T does not belong to T is not the case. We have supposed that T belongs to T. Since T is a set and T belongs to T, we have, or let me write it like this, T cannot be in T as an element. Look at this carefully. Since T is a set, and T belongs to T, in place of T does not belong into T, we have T belongs to T. So clearly the object T does not satisfy this condition fully. So it cannot be inside T. Okay. So T cannot be in T as an element. In other words, T does not belong to T. Now this is already contradicting what we have seen so far in set theory, that any object either belongs to a set or does not belong to a set, but not both at the same time. Here, however, this supposition that T belongs to T has led us to exactly its opposite. So you may say that, yes, I suspected this because this is a strange situation. It looks so wrong that it has actually led us to something wrong. So it should not be true. So that is cool, that is okay, because you felt that this is wrong and we have now justified that feeling using logic. So this part is over. Before justification, you cannot just simply say that this is wrong because I feel it is wrong. No, that is not accepted in mathematics. Now it is wrong, so we must have the other option. So our supposition is wrong and we must have T does not belong to T. This, however, looks quite right. According to our experience so far, this is the case. Any set that you can think of satisfies this. No set contains itself as an element. So this seems to be true. Okay. Anyway, So we have arrived at this. This is not an option at all, so this must be the case. However, let us explore what happens when we have this case. Here we have T does not belong to T. Now, T is a set. Remember where T is a set is coming from. It is coming from the rule method. The rule method says that any collection of this form is a set. Now T is a set and T does not belong to T. Now think of T in place of X. T is a set and T does not belong to T. So that means you can put T here. So that means T is inside of T as an element. But this implies T contains itself as an element. Let me continue from here. As an element, that is, T belongs to T. Now, here, however, our feeling that this must be correct actually has again led us to something wrong. Okay, so this rather hopeless situation is in front of us, and if you go through the logic, you cannot see any gap here in the sense that something is wrong. Our logic is solid. There is no gap here. The moment we have got this condition that T does not belong to T, because T is a set, automatically T satisfies the condition Px, this particular Px. So T must belong to T as an element, in spite of it not belonging to T as an element. Okay. This is also impossible. Now, unlike a proof where ultimately things are settled, this is a dead end, a cul-de-sac. Okay. From this dead end, there is no escape unless you change this supposition, the rule method, which says that any collection of objects satisfying some property always gives you a set. Unless you change this rule method, you at least have this this paradox, this impossible type of thing, which is a collection of well-defined objects which are distinct, of course, but still we cannot decide whether T belongs to T or T does not belong to T. So in the very beginning stages of set theory, where we first of all in sets we come across this belongings relation, and we cannot decide this simple thing here in this case. And what has gone wrong actually? What is about rule method that leads us to this horrible case? So this part is well understood. There is no escape from this T unless we change the rule method. But what is wrong with T? Let us try to think about that a little bit more in a slightly different way. Actually, the thing that is wrong with T is that T is extremely large. T has all the normal sets that we ordinarily see. All the sets, any finite set or any infinite set that we have come across, the important sets, the sets of all natural numbers, integers, rationals, real, complex numbers, all those sets are elements in T, and T has many more sets. For example, how do you create more and more sets from given set? Of course, you can take union and you can continue to unite sets, but there is a, what I try to say is that there is a better way of creating not only just more and more sets, but larger and larger sets. For example, you consider the set of natural numbers. Then you consider its power set. This is quite large. It has elements which are subsets of n. So if you think of writing the elements down in this case, you cannot even begin to think of the situations. What will you write? I think I have already discussed about this at one point. Do you remember we have made a statement like this? For any set A, P of A is in essence larger than A, and we have said that this is not settled until we get the concept of one-to-one correspondences. So it's about that. Pn is actually quite larger than n. You can keep on writing all the singleton subsets that you cannot finish writing. Then you will come across all the sets having 2 elements, 3 elements, 4 elements, any number of elements, but all of these are finite subsets of n. N has infinite subsets also. For example, the set of prime numbers, this is also a subset of n. So the set of prime numbers is an element of P of n. But regardless, we are not really concerned about whether this set is larger than this or not. What we are concerned about is that this set is different from this. Okay, this is not equal to this. Definitely it's not equal to this. And you can continue this. You can consider the power set of the power set of n. Then you can take power set once more, getting more and more large sets, progressively more and more complicated sets. All of these are sets, however, and none of them contain itself as an element. That, although is somewhat difficult to show as the complexity increases extremely fast. If you have to show, I think it can be shown that we don't have this set inside of it as an element. So all of these sets belong to T. So any set, any of its power set, in fact any set that you can think of belongs to T. So the size of T is so large, and it is so much larger than all the other sets of importance in mathematics, that leads to this peculiarity that this is, both of them seem to be true, or in other words, more correctly, we don't really know what is the case, whether T belongs to T or T does not belong to T. So how can we keep this rule method from creating sets like T? We have to clearly control X, not just with a condition, but with something else. And that something else is assuming that any object that you are considering in rule method, that is not just simply an object, it has to come from already another set. It has to come from some set, and then it has to satisfy some condition. This will allow us to avoid sets like T. In fact, there is a rule or an axiom in axiomatic set theory. It's called the axiom of regularity. What it says is that if we have a collection A which is a set, okay, if A is a set, if A is a not just a set, a non-empty set, if A is a non-empty set, then there is an element X belonging to A, which is either not a set or this. Now this may look somewhat quite arbitrary, and we really don't know at this stage why the axiom is like this and what it gives us. I mean, it says that if we have a non-empty set, then that set must contain an element X, okay, which is either not a set. For example, we can have something like this. We have considered situations like this before. So you consider this as A. If A is a non-empty set, then there is an element X belonging to A which is either not a set. We have such an element in A. Okay? Either that must be the case, or if all the elements are sets themselves, for example, suppose the one is not there here, suppose A is this, okay, then it must be disjoint with A, because you see, this is also a set, this is also a set. At least one of them must be disjoint with A itself, because we can consider the intersection. You see, is there any element in this intersection? In the first step we have 1 and 2, but they are not available here as elements. So this is empty. That's what this axiom of regularity says, that any non-empty set, either it must contain an element which is either not a set or is disjoint with the set itself. Actually, what it cares for, what this axiom of regularity says, is that you think of sets as constructed not using rule method which at once gives you very large sets. So in axiomatic set theory, we don't consider sets like that. We do that in stages. For example, first of all, you have some objects like 1, 2 numbers which are themselves not sets. They are called primitive objects. Then from them you can construct sets which have primitive objects as their elements. So that is the first rung in the hierarchy of sets. Then you can consider those sets which have in them primitive objects as elements, as well as the first sets, the sets in the first rung that you have got, them as elements. Then you move up the ladder. Okay, that way if you create sets, then you will never reach a T like that. You will never reach a T like this. Although to show that that is the case is extremely complicated, and these are the things that set theorists find about, or they study these things. and they have come up with an axiom like this which makes sure that that is the case. Okay, so this is the problem with intuitive set theory, that it allows us to consider some collections which are so large that the basic laws of sets start to fall apart. It's a situation which is somewhat similar to, I have already said that, Newton's theory of gravity. In ordinary situations, Newton's laws are extremely fine and they give predictions with high accuracy. But in extreme situations where gravitational fields are so strong that they bend the space-time around them, things like that are there, that the laws of physics start to fall apart. For example, in